So thank you very much for joining this scientific session on electronics and sustainability. So we'll be here for the next hour and a half, and we have 5 speakers lined up talking about various topics from digital health to batteries to various environmental sustainability related aspects. So it's a, a variety of different talks. So we'll briefly introduce them further, and then we'll call each person up to the podium to discuss further. And at the end of the session, there'll be a voting aspect for presentation, so we'll provide that information at the end. So I'm Rosie McDonald, from the International Telecommunication Union, and I'm joined by Pierre.
Yes, Pierre Humbert, consultant and former technical assistant for French Ministry of Transition, ecological transition, and EU expert for some conventions. Thank you.
And so we've got the format of you'll probably be used to the sessions by now. They're split into slot 1 and slot 2. And so for the first slot, we will have talks from Tamara, Akshat, Anita, and they'll be looking at different aspects of sustainable transformation of healthcare, design for recycling of paper-based electronics, and also the insufficient supply of cross-cutting materials for batteries, applications, and rare earth permanent magnets. So, and then the second slot, we will be having 2 speakers in that. So we've got Naomi Muindi from Ghent University and Martina Sarah from EMPA, and we'll be talking about the digital health devices, environmental sustainability of those, and also different lithium salts as electrolyte in lithium ion batteries. So very different aspects. So I think we'll dive into some technical, I'm sure we'll dive into some technical aspects of that as well. So I guess, I don't know if you've got any other things to, otherwise we can jump straight to the first presentation. I think we're down to 5 people now, so we'll have about 18 minutes in total per person to divide the time up, and we'll answer some questions.
Okay, Tamara, the floor is yours. 18 minutes.
Is this microphone on, or how does it work?
Or you can.
Or I can say just.
Maybe it's that.
Hello. Yes, that works. So, hello everyone. My name is Tamara Hoofling. I'm a PhD candidate at the Delft University of Technology, and I'm in the Faculty of Industrial Design. And my research focus is on how we can make the circular economy an accomplished reality for healthcare. So I will present some very early results, specifically focused on laparoscopic devices, and then give a short sneak peek of a report that's upcoming. So to add, my research is part of digital health in a circular economy. The DICE consortium, we have a stand at the conference, so you might have already spoken to some of us. If you wish to know more, go to circulardigitalhealth.eu. So what are laparoscopies? A laparoscopy is basically a minimally invasive surgery that doesn't need a whole patient to be sliced open, but instead just incisions of a maximum of 1.5 centimeters. And as you can imagine, this has many benefits for the health of the patient. And that's why they are performed more and more often, around 13 million procedures per year as we speak currently. Yet those devices are becoming more and more digital, so more electronics are added and they become more often disposable. So manufacturers introduce disposable devices to the healthcare sector because they say that it could be safer and there will be less infections. And in some cases, this is true. In some cases, this is just a perceived safety risk. But because of more electronics and more disposables, we also have more mining, more waste, and of course also more scarcity of materials and an increased CO2 emission. So we asked ourselves, like, how can we circularize those laparoscopic devices? And we needed to know what are the barriers and opportunities in doing this. So we did a rapid literature review and some expert interviews. And I don't have time to go in depth into all barriers we found, but the most common themes were safety barriers, financial barriers, systemic barriers, regulatory barriers, and technological and social barriers. And there are 6 ones of them that I do want to highlight because our participants actually told us that these were the most important ones. With on the top, the safety and infection risks, as I had already explained a little bit about. So there's, of course, high infection risks in healthcare. And in some cases, as I just already said, we feel like it's more about the perceived safety risks and not about the actual infection risks that are at hand. Of course, there are financial constraints, as in any sector, really. Also, the collection and separation of devices is a big issue. For example, when you have those laparoscopic devices and they wouldn't be disposed, then the healthcare workers need time to actually sort and collect them in the correct way so they actually come back to the manufacturer or any recovery facility. Fourthly, we have stakeholder interactions. We have a large network of stakeholders and they need to collaborate to make this happen. But we found that there is a lack of interactions connected with that these interactions don't always happen fluently when they do. For example, we use different terminologies. So when we use the same words, we mean different things by them. And in those interactions, it's very unclear who is responsible for the onset of the circular economy. So who takes the responsibility and who has the ownership of the device once it is in the circular economy cycle? And lastly, of course, health devices and especially laparoscopic devices need to be of extremely high quality. So for example, they need to be easy to clean, very complex devices that have lots of functions, which makes them, for example, hard to disassemble, hard to clean, etc. Fortunately, our participants also came up with some opportunities. Also, I don't have time to dive into them too deeply, but I will highlight the ones in bold because those were mentioned the most. So firstly, regulations are very important. I also already mentioned regulations to be a big barrier, but they can actually also help avoid those safety risks while still allowing the circularity. And as we can see on the next slide here, for regulations, we can actually make regulations that drive circularity instead of preventing it, and have regulations that create commitment. Then on the right here, lots of participants talked about spare parts. If we have a used device that is no longer in use, it often still contains some components that are useful to be used in other devices that are, for example, repaired or remanufactured. In the middle here, you see that what came up often is that it could be useful to combine different strategies. We see that in healthcare, often people focus on, for example, recycling or reuse, but we would like to see a combination of all possible circular strategies for each device, for as far as this is possible. And of course, motivational strategies are needed. And below that, as I just said, it's very unclear who is responsible. And our participants agreed that it should be the producers, the manufacturers, who should take the responsibility for their own wastes. Then a short sneak preview of a report that's upcoming that I would like to share with you. So by the end of this month, via DICE, we will release a report, not focused specifically on laparoscopic devices, but on the whole wide scope of digital health devices. It will have an inventory of best practices of circular digital health devices, barriers and opportunities, and potential design requirements. So if you want to wish more, stay tuned. And once again, maybe follow me on LinkedIn or go to circulardigitalhealth.eu. Thank you.
I start? Okay. Thank you very much. What is the total? Oh, my name is Hauke Schleser, EMPA. My question is, what is the total mass of this instrument that go to waste each year?
Well, it depends a bit on how many devices are actually disposable, because some of them are just partly disposable, that only dispose like the front part. But as I just said, I know that there are 13 million procedures performed yearly, and they use one device for each procedure. So I think it would be close to that number of devices that is disposed after the surgeries. Does that answer your question?
And what's the mass of one device then?
I wouldn't know exactly.
Yeah. So I could perhaps add on to that. So one device is approximately 1.5 kilo.
Okay.
Mostly high grade stainless steel, which is very valuable. So it's not your average stainless steel. It's pharma grade or medical grade steel, which is really valuable. And then of course all the electronics that go inside it as well.
Okay. Thank you.
Yeah, also Akshat from EMPA just had a question about if there's any conflict between the medical and the biohazard waste management regulation and the WRRE management regulation. And for example, if, because I think your colleague just mentioned that it's very valuable stainless steel, right? I think the regulations are very general and not very specific. So how do usually the hospitals deal with this confusion? And what is essentially done right now is that they send them for biohazard treatment or incineration and then landfilling probably, right?
Yes, that's correct. What we do see often now is that just in case something is infected, they just put it in the medical waste bin, even though when it could still be not infected or hazardous, just to be sure and just to make sure that they don't overrule any regulations. They just let it be incinerated currently.
And then maybe on your point on WRRE directive, currently this exempts the medical waste. So even if it has EEE products, they do not fall, they are not covered under the WRRE directive.
Yes, good addition. Anyone else who has a question? Yes.
I have a question. First, a remark on infection risks. It's the same movement in French hospitals to reduce the costs. If an expert, a physician says that, and knows that his patient is not infected because he has a heart disease, then the material is most probably not infected and will not go to the expensive and lost infectious way. But well, I have a question about extended producer responsibility, because they are electrical and electronic equipments. There are many reasons. Does it work? Is it in place? What happens? And all the ways of managing waste, reuse, repair, and so are included in the waste management policy of EU under the responsibility of the producers. So where is the problem today? Thank you.
Yes. So we see this issue mostly for discussions about devices that are currently not circular. And what we do also see is that there are some upcoming businesses that actually take the waste from the hospital, for example, which are external parties, and then refurbish the devices and sell them, which means that the producers lose the ownership over the devices. And then they also lose, of course, the financial benefits to the selling of the reused devices. So that's where we think it could be also financially beneficial to actually have the ownership stay with the manufacturer.
What do they think about that idea? The manufacturers.
The ones that I have spoken to were positive.
And maybe if I can add on that on the EPR, what we do see is that even when you set up voluntary take-back schemes, which effectively should be accounted for in current EPR schemes, this is not. So you're actually having double costing. So there may be some, there has to be some sort of system or crediting or something like that, which would stimulate people to do the take-backs in the first place, because now there are sort of, it works both ways really. So that's something we do see in the industry.
Maybe just add another question more about the regulation side. So I am not familiar as such with the healthcare aspect and like the directions it's going, but I guess it might be similar to the wider e-waste side. But have you seen any changes in recent years with the way the EU is introducing more regulations, and maybe even with COVID? I think that shed quite a lot of light on this very disposable culture. So I don't know if that's changed mindsets a bit. Thanks.
Yeah, we do see some recent changes, but I should say that regulations are not my expertise. So maybe one of my colleagues wants to take this question.
So I think the regulations, the ones that are in place, we have the updated packaging waste regulation. First of all, we really are happy that this is a regulation, not a directive. It will harmonize a lot. Eco design, similar. I think we're all quite supportive of that because it will give a level playing field across all sectors. So I think we're quite supportive of that as a whole. What we do see is that some of the regulations in terms of the medical device aspects of it are not necessarily aligned with the more sustainability driven regulations. It's part also of the review that Tamara has been doing, where we do see barriers. Again, collecting the devices back and trying to get them across member states to somewhere else for disassembly is simply a nightmare today. So I think there's opportunities to improve and to get them aligned. Beyond the transport, also indeed convincing health authorities that it's safe to reuse the parts is another matter. So we need additional controls in place to allow that, and where we also see a sort of out of sync between the drive on the one hand and the safety on the other one.
Yes. It's always a balance between risk and advantages, and the question is to take the responsibility and not to apply unlimitless precautionary principle. Then we recycle nothing.
Good morning, everybody. I'm Akshat from EMPA, and I'm here to present the topic of the need for design for recycling in an upcoming field in electronics, which is for printed electronics. So this is some work that was done under funding from the European Commission as well as the Swiss Secretariat for Education and Research. And yeah, let's dive in directly.
You can use the mobile microphone if you prefer.
Is it working? Yeah.
Yes.
Okay. So there's a paradigm shift that is being envisioned in the electronics sector. And this is a result of novel printed electronics that are slowly coming up. Before I jump into what are novel printed electronics, I want to first quickly go over the subtractive manufacturing process of conventional printed circuit boards that are prevalent in all conventional electronics that we see everywhere. So conventional printed electronics are usually manufactured by taking a substrate material which is usually made of glass fiber or epoxy that is coated with a sheet of copper, and then using a stencil, essentially the circuit design is etched away, and that's how you get the final conductive tracks that you see on the substrate. In comparison to the subtractive method where you actually add material and then remove the excess, there is an additive manufacturing process, which is shown here for printed electronics. So you start off with the substrate. In this case, it's paper that's coated with a film of nanocellulose. And on this substrate, you directly print the circuit design using conductive inks. And in this example, this ink is based on nanosilver. So there are a few advantages of using additive circuit manufacturing over the subtractive one. One being material efficiency. So you don't use up as much material as you do in subtractive manufacturing because, of course, you add material first and then remove the excess. So you reduce the number of process steps. The second being the elimination of the chemical etching process, which requires a lot of corrosive chemicals. And as a result of this gives you a lot of flexibility when it comes to selection of substrate material, because now you're not just dependent on chemically resistive substrates like plastics and polymers, but you can also be more versatile with, for example, biodegradable and bio-based substrates, as a result of which you can theoretically have biodegradable electronics. Another advantage is, of course, monolithic integration. So just like you print the circuit design directly, you can also print circuit components like resistors, capacitors, and displays directly, and do away with an extensive supply chain that usually comes with electronic components. And finally, you can also be sure that those components in which you do not require flame retardants, you avoid the use of brominated flame retardants. So where are these printed electronics used? So the paper-based electronic system that you saw right now was actually developed in an EU project called GreenSense, and they developed essentially a quantitative drug detection system that had a biosensor at the bottom of the device, which used saliva to detect drugs. There is an entire paper on this, so if you are more interested on the topic, I would request you to scan the QR code. But apart from GreenSense, now there are other general applications that are also possible with printed electronics, particularly low voltage applications in environments with low humidity. So for example, clocks, radios, computer mice, and computer keyboards. There's also a paper that we came out with on the possible applications for printed electronics. So please scan the QR code if you're interested in learning more about that. I will just give people 2 seconds. Okay, maybe I will switch. So in this assessment, what we wanted to do was compare these novel printed electronics with conventional printed circuit boards and assess if there are any sustainability advantages when it comes to global warming footprints. So we applied the cradle to grave LCA methodology, starting at, of course, the production phase, the use phase, and the end of life of both printed circuit boards and printed electronics. And we came up with the carbon footprints essentially for the entire life cycle of both. So we have printed circuit boards and printed electronics on the x-axis. And what you see is the change in the share of conductive area. So the larger the conductive area will be in a circuit, the more ink you would require to essentially print the circuit design. So that would have a bearing on the environmental impact. So we've modeled different conductive areas. And in this graph, essentially, you see the top parts are the conductive parts. So the copper in the conventional systems and silver and silver inks in the printed electronics. Also, the bottom parts of the graphs are actually for the substrate, so paper and the glass fiber and epoxy resin substrates. For printed circuit boards, what you see, the green substrates, which are the glass fiber and epoxy substrates, actually have a very high environmental impact in the manufacturing process. And this is a consequence of the high energy intensivity of the manufacturing process. So therefore, when you compare it to conventional paper, there's a big environmental advantage that comes with replacing flame retardant substrates with paper. But these advantages for printed electronics are somehow really outweighed by the high impacts of the conductive material, which is silver. So they rely on silver-based inks for high conductivity. And because silver has a very high mining and sourcing impact, we see that the impacts of printed electronics are very large when you compare them to printed circuit boards. And we see that any sustainability benefit, at least from a global warming perspective that you saw for lower share of conductive areas, are essentially removed by the time you exceed a conductive area share of 25%. So the larger area that you need to essentially print means that you don't have any sustainability advantages. But this was one of the results. So what we realized was essentially making biodegradable and compostable electronics for decay in the environment is maybe not as environmentally sustainable as people think. As a second part of this assessment, what we did was that we decided to close the loop and do a closed loop modeling of both the electronic systems. And we assumed that metals like silver and copper are recycled in a closed loop. And the results changed quite drastically. So you can now see that the impacts for the metallic parts, which are recycled, are significantly lower. And as a result of this, the printed electronic systems really benefit when it comes to the global warming footprint. The substrate impacts, of course, don't change because the substrates are not recycled. And therefore, here we actually see that recycling of printed electronics can help in ensuring a consistent sustainability advantage over the complete life cycle of the systems, irrespective of the conductive area. Therefore, this just brings me to the conclusions, which is that, yes, biodegradable electronics and bio-based systems are being developed to deal with the problem of persistent e-waste and mismanagement of e-waste. And it does make sense to look for alternatives when it comes to the substrate and the glass fiber and epoxy material in conventional electronics. But designing electronics that are meant for mismanagement and maybe just release into the environment is not the right approach. So developers of these novel electronics and material scientists really need to be more aware of the waste management and e-waste management systems. It's required that they design their products with the idea of having recycling in mind, because that is truly when you can come up with more sustainable solutions. And with that, I come to the end of the presentation, and thank you for your time and attention.
Does anyone have questions?
Yes. Thank you very much for your presentation. Els de Schenne, DICE coordinator and from J&J. I just had one question. Did you also check other endpoints than global warming?
Yes. So we did check ecotoxicity. So the results didn't change too much. The trends were similar, identical. And we did it for ecotoxicity as well as some aggregate environmental categories. We decided to do global warming because the target audience was actually material scientists for the paper. So we're trying to communicate with them, and it's somehow more easily understood by the material scientists. Yeah.
How is this more durable than the current PCBs that we already have?
So durable, that's the challenge. So the idea is a lot of the PCBs that we have today, especially in some applications, may be an overkill when it comes to their capabilities and durability. So for a lot of single-use electronic systems, probably in the medical sector, it maybe makes sense to look at these sort of alternatives where the materials are low impact for sourcing. So when you dispose them and discard them at the end of life, they don't have a very high impact. That is somehow the intention behind the development of these electronics. So it's for applications where durability isn't a problem, and then environmental humidity is low because the materials are, of course, biodegradable. So they want to make sure, yeah.
Won't that require the user to keep on changing it regularly?
Yes, but it really depends on that.
Isn't that not cost effective?
Yes, it depends on the application. That's the thing. So, for example, the application developed in this project was a single-use application, for example. And there, it probably makes more sense to use paper as a substrate rather than conventional fossil-based epoxy and glass fiber. Because, yeah, there the impact would be actually quite high if you stick with conventional systems.
I also had another question. What are all the different limitations that you came up with, like that you had to face when you had to come up with this, other than just durability and
No, there are quite a few. So firstly, also because they're still trying to optimize the systems, they're very dependent on silver for the inks. They want to they want to change that and probably shift to copper, but there are technical difficulties because nano copper oxidizes very fast and then the conductivity decreases. I mean, one thing that was very interesting for me was that, I mean, I was always under the impression that graphite is a very good conductor of electricity. Apparently, that's not the case. So that was one thing. So it's very hard for them to actually come up with metal-based conductive inks. That's now the challenge, and the goal is to actually move away from the use of silver. That's somehow what the developers are actually now targeting. Mhm.
Okay, so thanks for the very interesting presentation. Actually, maybe it's too early to say, but I'm interested in the costs or maybe the perspectives on if it's really a low cost alternative. Do you have some idea about that? And about the technology needed? Where can you find the technologies to produce this kind of alternative?
Yes, so I will start with the technologies. The advantage is that it could be manufactured by conventional printing route. So just think of having a piece of paper and then you can actually just print the circuit design directly on it, like very complex circuit designs essentially. And also the circuit components, resistors, capacitors. Um, so you just need a printer and then the specialized inks. Now, inks would be where actually the technology limitations would probably be. So that's the technology side. But the idea is that it can be done without the need of a very large factory, which would be the case in conventional electronics, that you need a very large wafer factory that they manufacture the circuit boards and then they produce them. So that's the challenge. For the cost effectiveness, we didn't come up with cost effective estimates right now. This device, they estimate they can produce for €2. But I think it's very early to say, and it's specifically quite early in the innovation stage when it comes to the technology readiness level. So those are still challenges that they're trying to look at. Yeah.
Did you perform uncertainty and sensitivity analysis to see how robust and certain the results are?
This was also the problem because the data to do an uncertainty analysis was not available. What we did do was that we tried to actually do a hotspot analysis essentially to see the results that we have, to what extent would they be affecting the final results. So for each component, yes, we have an article in one of those QR codes that does somehow look at the sensitivity of the final result to the input materials and the input components, but not explicitly a sensitivity analysis.
Yeah, thank you for the presentation. Could you please elaborate a little bit more about the need to add flame retardants?
Yes, so it's, I think, in the similar direction to the functionality of the electronics. In a lot of applications, maybe it's an overkill. We have too much function. So maybe the conductivity of the circuits are too high. The durability that they are being designed for is too high. And then also, if they're being designed for flame, they may be used in applications in which there is no fire risk or minimal fire risk. So they don't really need to add flame retardants there. And the problem with flame retardants is, of course, that at the end of life, it becomes a problem for recycling. And I think the legislation now says that if the circuit boards have flame retardants, they need to be treated as hazardous waste. So that's the reason for the elimination of flame retardants. And of course, if the electronics are mismanaged, then the flame retardants leach into the environment. So those are the challenges. But there may be cases in which you don't require flame retardants, and we are trying to maybe overcompensate for the required functionality. That's maybe something that developers need to think about. Sufficiency when it comes to actually the application. If what you're trying to produce, if it's just sufficient, or are you doing too much and in the process using more resources and materials?
I have a very short remark, and then we will have to close. You speak about disposed or discard after use. No, that's the old world. You should make a separate collection and recycling of silver.
100%, yeah.
Thank you.
Yeah.
Hi, my name is Anahita Jannesarniri. The topic of our study that I want to present here today is insufficient supply of cross-cutting materials for batteries applications and rare earth permanent magnets, the neglected serious risk. Actually, I can say that the topic of my study has changed, but it's fine. I mean, actually, it's not the file that I sent but it's okay. Okay, the topic is insufficient supply of cross-cutting materials for batteries applications, which is a neglected risk to the green transition. And this is okay. Copper and aluminium, also known as cross-cutting materials, play imperative role in electric vehicles and energy storage systems. But like other raw materials that are used to manufacture green energy technologies, there are also challenges that can disrupt the sustainable supply of these materials, including geographical distribution, ESG complexities, geopolitical issues. For example, in Chile, in 2019, the production of copper decreased due to lower ore grades, strikes, and weather-related disruptions. And in China, in 2021, there were shutdowns of power plants and consequently increasing aluminum prices and increasing coal prices, which gave rise to geopolitical and economic vulnerabilities. In this study, we want to evaluate the future production of these materials, production of copper and aluminium. In this study, we want to evaluate the historical mine production of copper and primary aluminum production to see the challenges that disrupted the sustainable supply of these materials. And to do so, we collected data on yearly production of copper and aluminium from 1980 to 2022. And to collect the data, we use British Geological Survey and United States Geological Survey. And to do the forecast to predict the future production of these materials, which is one of the main prerequisites to actually anticipate the dynamics of clean energy, energy supply security, we use three different methods: seasonal autoregressive integrated moving average, Halt's linear trend method, and Halt-Winter methods. Our modeling strategy has 3 steps. The first one is a verification step to find the model parameters that fitted our data set. And the second, validation evaluation. To do so, we used in sample forecasting technique. And finally, doing the forecast for the next 20 years. For the results related to copper production, we put the world total production of copper as an example. And as you can see, from 1980 to 2022, the production of copper in general increased. Of course, there were some challenges that disrupted the sustainable supply of these materials. For example, in 2017, due to lower ore grades and depreciation of US dollar and the general lack of new project and expansion plans, the production of copper decreased. And also in the forecasting part, which is this gray area actually shows us the confidence interval area, and we considered 95% confidence interval. And this is also the different methods that we use: Sarima, Halt method, and also Halt-Winter method. And for both Halt method, we use both normal trend and damped trend. As you can see, based on the result that we got from the forecasting methods that we use, the future production of copper will increase. And when we compared our results with other studies and also with real worlds, we could say that, okay, the result that we got and the methods that we use are reliable, because we know that now around the world in different countries, there are new projects and expansion plans. For example, in Democratic Republic of Congo, in Chile, Peru, and Russia. But we shouldn't forget that, of course, in the future, there would be also different challenges that can disrupt the sustainable supply of copper. And also it is considered that because of the actually the lack of high grade, high quality and larger scale projects in pipeline, actually the world market is likely to turn into deficit, especially due to the Chinese economy recovery if it happens in the future. And also we put the table showing the compound annual growth rate of all the countries during this period of time that we considered. And for aluminum production forecast, we put the results belonging to Australia. As we can see, from 1980 to 2011, the production of aluminum, primary production of aluminum, increased in general, and from 2012 to 2017, the production decreased because of different reasons. For example, lower demand for aluminum, high coal prices, power failure, and etc. And when we look at the forecasting part, the primary production of aluminum will decrease based on the results that we got from the methods that we used. But when we look at other studies, for example, the actually reports released by Australia's government in 2024, the production of primary aluminum is planned to reach 1.6 million from 2023 to 2024, which is more than actually 1.5 million in 2022. So what's the reason of these differences? I mean, we got downward trend, but is projected that the production will increase. Actually, it's because of the lack of data, the problems that I think all of us came across during our study. And also, because when you don't have enough data, the model is not able to capture the actually inherent patterns in the data points or interesting internal structure of the data. So the models that we use identified the downward trend more important going to the future. So that's the result that we see this downward trend in the forecasting part. For aluminum also, we put compound annual growth rate of all the countries that we included in our study. And as I've mentioned before, we also have validation evaluation step. So this step helped us to compare the reliability of the different methods that we used. So to do so, we divided our data points into two different groups. The first one as actually training part, and the second one as test part. We used actually training part to find the parameters of the models that we fitted to our data points. And for the test part, we predicted the future values. So then using the evaluation metrics, including root mean square error and mean absolute error, we actually compare the predicted values and observed values. And the lower value here actually means higher reliability. So for both aluminum and copper, Sarima has the highest reliability. And for aluminum, Halt linear trend is more reliable. Halt winter method is more reliable than Halt linear method. And for copper, it depends on this because, as I mentioned, we use for both normal trend and damped trend. So for these Halt methods, when we didn't use actually a dampening parameter, Halt linear is more reliable. And when we used a dampening parameter, Halt winter was more reliable. So as you can see, actually, we cannot just pick one model and say that, okay, this model is reliable. It can change. It depends on the data set in the characteristics of the data points that we have. And finally, by coupling the results of the study that actually we have done and future plan studies, we can actually create a comprehensive framework by using which actually comprehensive scenario can be developed. And in this framework, to be developed, there are some factors that should be considered. For example, repercussions of the current approaches to the sustainable supply of critical raw materials, environmental, social, political, and economic objectives should be considered, and regulatory systems to support the value chain without jeopardizing sustainable development goals should be analyzed. And finally, the often difficult trades-off between various dimensions of sustainability at the local level and an international level can be managed. Thank you so much.
Thank you very much, Anita. Thank you. And I think is there any questions on the floor?
Yeah, Akshat from EMPA. Thank you very much for the presentation. My question was about the degrading ore grades. Was that modeled in the study as well explicitly?
Model to consider what?
That there would be a degradation in ore grades over time because the more ore you extract,
that you can capture by the model that you can use to capture these characteristics of the deposit, you mean?
Yes.
Actually, it's a data-driven exercise. The model that we used. So they just consider the data that we gave them. So these models don't have the ability to, considering, that's a decreasing characteristic for the whole period of time that we want to consider or use to do the forecast.
Yes, and I was asking this question because you model. Sorry.
Actually, when you did the forecast, you can use the historical data, and then you got some results. And then the next part is actually the frameworks that you want to create. Okay, when you want to explain the future events, then you can consider, okay, I found that the production of copper will increase in the future, but I have some situations that is going to happen or will happen in the future. That's the place that you can consider decreasing ore grades of different materials.
Mm-hmm. But I was asking the question because your assessment was for primary production of metals, exactly, right? Or also did they include the secondary production?
Yes, actually it depends on the availability of data. For example, for copper, we had mine production of copper, the metal contents in the ore deposit. But for aluminium, we didn't have such a data. Mm-hmm. So we had to consider primary aluminium production. Mm-hmm. And it depends on the material and data availability.
Okay, thank you.
Sorry, Jan Rosenkrantz from Luleå University of Technology. Just to add to that, we have the historical data, and some they show then some trends, and you saw also differences. Some were only going up, others already over the peak. So this is, of course, then information that will then control the further calculation. But also for copper, it's always said it's lower grades and more complex mineralogy, but you still see that production is increasing. Yeah, so this is something that is maybe then compensated by more efficient technology, and also then going for more projects in order to cover the demand. Yeah, so this is something. In Sweden we have one copper mine that is having grades of 0.2 to 0.25% copper, and they still make a profit out of that. Yeah. So therefore, some development will continue as it is, because there will be more effort in that.
Yes. Because we were a part of a study, and what I think our study found was that eventually the secondary metal market will somehow overtake the primary production.
Yeah, it was yesterday also a presentation from a colleague from China, where they did a life cycle analysis. So we have done it also at LTU maybe 15 years back, and they're given the prognosed demand or increase of demand, we came to the conclusion that there's still the need for primary production for another 60, 70 years before there's enough copper in the system to then feed from secondary sources.
Great, thank you very much, and thank you, Anita, for your presentation. And so that's the end of the slot 1 sessions, and we'll move on to the slot 2 sessions now. And we've got 2 speakers for this slot, and the first one is Naomi Muinde from Ghent University in Belgium. So thank you very much for joining us today.
Yeah, thank you. Yes, so my name is Naomi Muinde from Ghent University, and I'll make a presentation on the challenges of evaluating environmental sustainability of digital health devices, and it's a systematic review. The project, we are trying to come up with recommendations on how to do life cycle assessment of 4 products. That is part of the DICE project, and you've seen the booth outside. So I'll just start. There are so many challenges in the healthcare sector in the last few years, such as aging population, healthcare inequalities, epidemic and pandemic, as you saw with the COVID-19, and also high healthcare cost. And this has prompted a lot of technological innovations, and some of them come in form of electronic health devices or electronic digital health devices. And these devices have a lot of benefits and advantages, such as reliable diagnostics, as compared to conventional devices that were used before, self-monitoring capabilities, such as the wearable devices, improved patient comfort, and also less invasive procedures. And when you're talking about surgical electronic devices. However, with the benefit also comes the environmental impacts. At the moment, we know that healthcare sector contributes about 2 to 5% of the global carbon footprint, which is very high. And when you're talking specifically about the hospital setting, if you zoom in, 70% of the waste comes from the operating room. So this is a lot of waste. And part of it is medical equipments or electronic equipments. And this is because most of them at the moment, they're not circular because of the perceived risks of safety, as Tamara mentioned before. Also, their production leads to high emissions, and also they can lead to metal depletion. So many recommendations have come up in terms of circularity strategies of these devices. For instance, there have been a replacement of single-use surgical devices with the reusable alternatives. We've also seen reprocessing of surgical devices. Not all of them can be reprocessed, but some of them can. And also other strategies such as repair and remanufacturing. However, because this is a new area, these are new technologies in the market, very few research have focused on this specifically. And this prompted us to come up with a paper to focus on this area. And the objective was first to investigate the current state of knowledge on environmental assessment of electronic healthcare devices. And second, identify if there are any research gaps and offer recommendations from the perspective of using life cycle assessment. We used literature review. So we had 3 databases and a lot of keywords combinations, for instance, electronic healthcare devices and life cycle assessment. And we were able to retrieve more than 2,000 papers. And after 3 steps of screening, where we excluded most of the papers because they were maybe out of scope of the healthcare system, or they're not related to environmental sustainability. or the qualitative studies. Some of them were actually not, the medical devices were not related to electronic healthcare devices. And at the end, we ended up with 17 papers. Then we decided to categorize them into two because some of them covered surgical electronic devices, while others covered the non-surgical electronic devices. For this presentation, because of time, I'll focus on surgical electronic devices and the findings that we got. So as I mentioned, we did analysis based on the life cycle assessment framework. First of all, we did content analysis of the 17 papers, trying to find how the methodology they used, and we identified challenges based on the 4 phases of life cycle assessment, because most of them used life cycle assessment. Some of them used footprint method, only to considering carbon footprint. And also at the end, we offered recommendations in the based on the 4 stages of life cycle assessment. So for instance, for the goal and scope definition, we focused on 3 factors: the goal of the study, how they define the goal, they define the functional unit or the system boundary. And I will discuss about the system boundary, the findings that we got and recommendations that we have for it. So some of the papers, most of the papers that focused on surgical electronic devices, the goal was to compare single-use devices compared to electronic surgical devices. And this was most of the papers, this was the boundary that was set, which is a product level boundary, meaning that they only considered from raw material extraction to the end of life of the product. Some of them only considered raw material extraction or end of life and excluded some of the processes such as the use phase. And for the reusable electronic surgical devices, other processes were included in the analysis, such as reprocessing, repair, and refurbishment. However, there are some drawbacks of setting the boundary on the product level. This is because we only consider the direct impacts associated with the device. However, we know that healthcare electronic devices can also have indirect impacts. For instance, optimization of surgical procedures. When you're using, for example, a surgical healthcare device, it might lead to less invasive procedure, which also translates to less days in hospital. And we know that with less days in hospital, we mean less resources used. So if we don't consider the indirect impacts, then we are not actually considering the full boundary that we need to set. And other demand for other resources, because we might be using electronic healthcare device, but it might lead to a demand for another resource. But if we set the boundary just around the product, we are excluding such factors. And because of this, we proposed a recommendation. Instead of focusing on the product, we want to focus on the care pathway. So for instance, we start with raw material extraction, but then we also include the supply and services that are used during surgery. For instance, we can include other factors such as anesthetic gases, patient and staff travel, in addition to the electronic healthcare device. And then in the use phase, here, if I can go back, in the use phase of the product level analysis, most of the paper only included the resources that are used by the device, meaning that, for instance, electricity used by the device. However, if we decide to expand the system boundary to include the care pathway, which is the surgical care pathway, we also need to also include other factors in the use phase, such as anesthetic administration, because it might differ between products, and also include the postoperative stage, such as the hospital stay. However, this is also considering the goal of the study. And then we have the end of life. So why system level perspective in life cycle assessment of electronic healthcare device? Because we are considering the wider boundary of the care pathway, not the device. Also, it paints a comprehensive picture of the burden and benefits, because in the healthcare system, the value of the device is to increase or to improve human health. So if we consider only the boundary of the product, we are actually not communicating the entire or painting the entire picture of the burden and benefits of the device. And also, it takes into consideration the impact associated with service delivery. Therefore, in conclusion, our findings, we found that almost all papers that did life cycle assessment considered the direct impacts. However, we proposed in future, maybe depending on the goal of the study, we can also include the indirect impacts. And when you're talking about system boundary, specifically, system perspective is required. And the challenge, however, is going to be on data availability, because we're expanding the system, not only to include the product, but also the entire care pathway. Therefore, data availability might be a problem. Also, I want to mention that the results will be published, which is still in preparation. And other phases of the LCA were also done the same. So we have factors that we considered, and then the challenges for each phase of LCA and recommendations for these phases. Thank you very much. Any questions?
I have a question. It is not available, the trade-off and the life cycle analysis of anesthesia? Or do you have to dig from basic quantitative data of anesthesiant, of hours of people present, of conditioning of the operating room, and so on?
Yeah, recently there have been some studies, or I think the past 5 years, that are focusing on the specific, like anesthetic life cycle assessment of the surgical room. However, it also depends on a specific case. So it just depends on, maybe they do analysis based on a specific case, maybe a specific disease. So it might not be applicable to another case. Yeah.
So maybe if I may complement, because we are working in the same project, this is part of the sustainability assessment. We will have also the social assessment, and there we are considering these aspects that are being defined from different perspectives, depending on the stakeholder groups, patients, for example, and this will complement the sustainability assessment. So we are in work in progress.
Yes, and then maybe I can add something about what Sonia has mentioned. So expanding the system boundary can also be very important, especially if you're considering the social impacts, because we are taking the entire care pathway into consideration, not just the device. So we will see the impact of such devices on the environment.
Yeah, and maybe to further complement as well, what we do see, for example, in the UK, NHS has a clear pathway toward decarbonization. But if you focus at the product level itself, it may not be the best approach, because ultimately they want to reduce the footprint of the healthcare system as such. And by looking at the product itself, you might miss benefits. As if you were to compare to the entire care pathway. We've seen examples from that in other areas as well, for drug treatment, for example. If you move from, let's say, a 3-monthly injection of a certain drug to 6-monthly, you can reduce the footprint enormously, environmental footprint enormously, because of patient travel that is avoided, adherence that is increased. So that's what you're aiming for as a healthcare system. But if you would look at the footprint of the drug product itself, you would disregard it because it's slightly higher. So you have to have that sort of care pathway perspective overall to move in the right direction, which is really going towards that greener NHS, for example.
We have some minutes, so I allow myself to continue the discussion. First, we could use life cycle assessment for a given medical result. So because the zero action is the best, it's the zero impact action. So you put a medical result that must be achieved, of course. And as an environmental chemist, a concern is not to mix social criteria with technical or physical criteria, but because at the end, you mix pears and apples, and it depends on the expert judgment, what is the relative weight of the two parts. So I suggest you that you keep two separated appreciations or systems. Otherwise, you know exactly what is in the unique figure of impact, but it can be discussed endlessly.
No,
Thank you.
definitely, and I fully agree. And in the previous studies that were conducted outside of the DICE project, we did exactly that. So we just look at environmental impact, for example, and not start adding in social, but just looking at different ways of treatment, including no treatment, and that's actually part of our benchmarking as well. Was part of that, absolutely.
Yeah, thank you.
So we'd like to welcome up our last speaker of today, and this is Martina Serra from EMPA in Switzerland. So thank you very much, and you can use the microphone.
Hi everyone, I'm Martina, and
You've got the perfect.
And I come from HIMPA, they thought.
Speak in the microphone.
Yes, more closer.
Yes.
Okay. And today I will talk about lithium-ion batteries, and in particular on the electrolyte and the different salts present inside the electrolyte. So, oops. As you probably know, inside lithium-ion batteries, one of the main components is the electrolyte that is composed of a lithium-based salt, which is dissolved in a combination of organic carbonates such as dimethyl carbonate and ethylene carbonate. Typically, in conventional lithium-ion batteries used nowadays, the lithium-based salt is lithium hexafluorophosphate, which is also known with the acronym lithium PF6. However, during the recycling, so when the battery is opened at the end of life, the electrolyte enters in contact with the humidity of the atmosphere, and this lithium PF6 hydrolyzes, causing the emission of gases such as hydrogen fluoride. And this gas might be toxic. So on the one hand, there is the problem of toxicity. On the other hand, there is the problem of not being able to recover all the materials, because with current available technologies, lithium PF6 cannot be recovered. So the goal of this study was to assess the environmental impact of producing lithium-ion batteries with alternative lithium-based salt. For example, the lithium TFSI. And we analyze this through LCA methodology, so life cycle assessment, both producing lithium-ion batteries with electrolyte containing lithium TFSI coming from raw materials and from spent cells. To reflect the goal of this study, 3 different scenarios are analyzed. First of all, scenario A, that is the production of cell containing electrolyte with lithium PF6 that comes from raw materials. Scenario B is more or less the same while it has lithium TFSI coming from raw material. And scenario C is modeling the production of cells with electrolyte containing lithium TFSI that is recovered. Concerning the inventory, so the list of input and output of all the processes in the system, the inventory, so the data for the scenario A, so the production of lithium PF6 were already present in EcoInvent, which is the database that we used as a reference. Instead, production and recovery of electrolyte with lithium TFSI were not present, so we had to model this. This was done for the production with data coming from literature and additional exchange with experts for those information that couldn't be found in the literature. This is a list of reactions to produce lithium TFSI, starting using different compounds. You don't have to look at the reaction in the specific case, but I put them here just to highlight that when it is necessary to model a new compound, we need to reconstructing going backward until one compound is present in the database, which is in this case, the one in green. For the production of lithium TFSI, different assumptions are considered, such as the yield of the reactions, that is assumed to be 95%, and the remaining 5% of the emission is assumed to be end up into air. Regarding instead the recovery of the lithium TFSI, so what I mentioned as scenario C, we got data from laboratory experiments. So in this case, our colleague at EMPA performed experiments and we collected data from them. And then we upscaled this data at a hypothetical industrial scale by using the guidelines of the publication mentioned here in the slide. For this, 3 different main scenarios are elaborated, starting from scenario C1, that is a sort of worst case scenario, because it is upscaling the data coming from laboratory level in a proportion 1:1. So it results in a very high amount of solvent used, which is in this case water. And moreover, besides this, the recirculation of the water is assumed to be 90%. 2 other scenarios are modeled as a further refinement of this scenario for C1, and these 2 are C2 and C3. They are consisting in a lower amount of water used, so the solvent, which is 30 kilo, and the difference between the 2 is about the recirculation of the water, which is assumed to be 90% and 100%, respectively. The results are calculated through the LCA, so through the environmental footprint method, in this case, the version 3.0, at the midpoint level. And here you can see the results for producing 1 kilo of electrolyte by considering scenario A and B, so the production of lithium PF6 and lithium TFSI from primary materials. I'm sorry if the graph is a bit small for you, but yeah. And you can see the colors. So darker colors refers to the impacts of producing the salts. Instead, lighter color refers to the impacts of producing DMC and EC, and these 3 are the components of the electrolyte. And as you can see, the impacts for producing the salt is higher compared to the impacts of producing the 2 organic carbonates, even if the salt is present in a lower quantity inside the electrolyte. What can you also see as a general trend is that the production of this electrolyte containing lithium TFSI produced according to this way we modeled as lower environmental impacts for the majority of the impact categories, but not all of them compared to the production of the electrolyte with lithium PF6. The same analysis is performed at the level of the cell, just for a comprehensive analysis. And you can see here the trend is maintained, but the results are more flattened because inside the cell, we don't have only the electrolyte, but we have other components such as the anode and the cathode that are also impacting. And the electrolyte, as it is mentioned here, is only 11% of the total weight of the cell. If we had also the scenario related to the recovery, we can clearly see that the production of 1 kilo of electrolyte with lithium TFSI that is recovered has much higher environmental impacts. The same graph is reported that, but without the scenario C1, because scenario C1, as I mentioned before, was a sort of worst case scenario. So the impacts are sort of exploding. And there you can see that even by considering the refinements scenarios, so C2 and C3, the production lithium TFSI recovered, so the electrolyte with this lithium TFSI recovered has still higher impacts than the production of the 2 salts primarily produced for the majority of the impact categories, not for all of them. The same analysis is performed at the level of the cell, so I'm not entering into details again, but the results are more or less the same. So as a final consideration, after this evaluation of the environmental impact, these potential environmental impacts of using lithium TFSI inside the battery that is also recovered and not only primarily produced, we can say that for the production, there is at the level of the cell, slightly lower environmental impacts for producing the cell with lithium TFSI that is with lithium TFSI instead of lithium PF6, but these differences are not so big. And at the level of the recovery, there are much larger impacts to produce cell with lithium TFSI that is recovered according to this way of recovering lithium TFSI. This is because the process is using a very high energy, so they are very energy intensive due to the high amount of solvent. So one option, one further outlook could be to analyze other processes that can use a lower amount of energy. Thank you.
Thank you very much, Martina, and thank you for all the speakers. But just ask if there's any questions for Martina. We've got about a few minutes before we need to move on to the voting and any final marks.
We have time. Yeah. So.
Oh, I have two questions, Martina. Thank you for the presentation. I really understand the composition of the cell. You mentioned lithium, tin, fluoride, sulfur, and maybe indium. That's correct?
You mean lithium DFSI?
Yeah, the composition of the salt.
The electrolyte is in a composition 3 to 7 with EC and DMC, and the salt. Exactly the composition of lithium DFSI, I don't know, but I can check and let you know, because I have to check the specific compounds of this compound. I'm not a chemist, so
okay. Yeah, okay.
This was difficult for me. Yeah. It was the most challenging part of modeling the compound.
And the second question is the study that you did is considering maybe an economic feasibility?
No, not at the moment. It's just only about environmental impacts, because the process was also developed at the level of the laboratory. So we would also try to understand if it makes sense from an environmental point of view and not from an economical point of view. But it could be analyzed. Yep. Thank you.
So how is this better than hydrogen fuel cells? Since we are going to a better future where we are incorporating hydrogen fuel cells, how is this better?
I have to say that I'm not expert on these hydrogen fuel cells, so I'm not really able to answer to your question. I can say that we try to analyze these different electrolytes containing this lithium DFSI to try to solve one problem related to this emission of HF. But yeah, I'm sorry.
That's okay. Thank you.
Okay, so maybe a comment. This is an interesting case where potential recycling is less interesting than what burning in industrial furnaces, stockpiling stabilized with calcium fluoride and stockpiled forever in hazardous waste landfills, or what is the alternative?
In this case, the results were like this. We did some assumptions, so it is possible that considering also different assumptions, the results could be different. This was based on what I found on the literature and what I got through exchange with experts, because I also analyzed the possible recovery of the lithium PF6, so the other salt that is now used, and I couldn't find really so much information in the literature. I don't know if the other option is like expose
but
them.
In fact, I don't. Somebody knows in the room what is the chemical way to recover lithium today?
No, actually, sorry to interrupt.
Yes.
Lithium is recovered. It's not recovered lithium DSI itself. It's recovered lithium that is present inside the cathode, and there are a lot of ways to recover it, like different processes. They are also now trying to use this direct process to recover the material, and it gives quite good result at the moment. So it's not recover the salt itself inside the electrolyte, which is typically lost.
So, but they have to transform the lithium phosphate fluoride into a lithium salt.
Probably, but some.
So there is a technology today, but not recovering the original compound, but at least the mineral.
Yeah, but we were also told with Eleonora, she worked with me, that this lithium PF6 was lost during the processes of recovery, and also it's such a small quantity that probably doesn't make sense to do a specific process to recover this. Maybe she wants to also add.
Yeah, may I add something? Yeah, Eleonora from EMPA. Actually, I just want to make explain a bit more that this lithium TFSI actually is not yet used in industrial cells. So we are trying to anticipate a problem somehow with our research. I mean, it's a very preliminary research based, as Martina clearly said, on experimental data, so at really lab scale. And I mean, at the moment, lithium PF6 is the typical salt that is used in the lithium ion batteries. And ideally, the first step would be to try to find a way to recover this type of salt. At the moment, nothing really exists. There are some companies, as far as I know, in Germany that are trying to recover some parts from the electrolyte, but the focus is mostly on the organic solvents. It's not about the lithium salt. This is basically lost because it's not a huge amount inside the cell itself. And lithium TFSI, the problem is that it's not yet stable enough inside the cells on a bigger scale because you need some additional material to protect basically the anode and cathode from corrosion. This is something that it's to be studied as well. So we somehow are trying to anticipate a potential problem that we might have in few years. I mean, since the world of lithium-ion batteries as like the research and the use is evolving so fast, so we need to be a bit, looking at the future, not just what is happening nowadays.
Very good, very good. Other questions? No. Okay, thank you. So we are on time, so we can have some minutes discussion, and then we will vote. You with your phone, you can vote on and note the different presentations. So, are there some general discussions or comments or? No. Okay.